Hello, everyone, and thank you for joining us today to this session. So today, myself and my colleague, we are going to talk about our learnings and experience with integrating Apache Kafka with Istio on Kubernetes. So just a bit of history on us, where we started and what we wanted to achieve that led us in the end to integrate Apache Kafka with Istio. So originally we were working for a small startup called Banzai Cloud that was just recently acquired by Cisco. This is why you are seeing the Cisco logo on our slides. But back then we were looking at trying to use Kafka as a messaging backbone for our services. And we were interested to run Kafka on Kubernetes in order to leverage all the various advantages that Kubernetes can provide in order to have a much stable Kafka cluster compared to the capabilities provided by an on-prem setup where you can't easily change disks, machines, and so on. We looked around at what was available at that time on the market in the open source space to run Apache Kafka on Kubernetes. Most of the solutions were based on stateful sets deployed with Helm charts. And we were not that happy about the capabilities provided by those tools. We thought that we cannot achieve all the goals that we wanted. So we decided to write an operator, so basically to write a product, to implement a product that would do the operation of the Apache Kafka cluster on Kubernetes in such a way that it provides something in terms of scalability, resiliency, security, observability, and disaster recovery. So our goal was to be able to deploy, upgrade, so basically to manage the whole lifecycle of a Kafka cluster on Kubernetes, being able to run in parallel multiple Kafka clusters if you wanted on the same Kubernetes cluster, assuming that the Kubernetes cluster is big enough in order to fit in multiple Kafka clusters. We wanted to automate as much as possible in order to have scalable and resilient Kafka clusters. Also perform rebalancing behind the scenes of the data in the Kafka cluster, again, to make it all the time as close as possible to the kind of the ideal setup to make it resilient and high performing. Also, the security part was an important part there. So we wanted to ensure that all the components that are required to run Kafka on Kubernetes talk to each other using secure channels. So basically encrypted channels using SSL. The various workloads here that play a role to be identified and also authorized to allow only just to perform operations that they should be allowed to do. Now we know that Kafka supports different mechanisms so various mechanisms for authentication and authorization. Out of those, we decided to go with the two-way SSL authentication authorization because we thought that gives us enough guarantees in terms of security compared to the other mechanisms that are available in Kafka, like SSL and so on. So besides security, also observability was an important bit there. What can we do to monitor everything that we deploy, and also to be able to have appropriate alerts, and also automatically execute certain operations based on those alerts in order to have a self-healing functionality there. And also we were looking at disaster recovery, in fact, leveraging the mirror maker tool capabilities that was provided by Kafka. So this was in kind of a nutshell that what were the requirements, what were the goals that we were trying to achieve with this product to run Kafka on Kubernetes. Now, we are going to expand on security, because there is that's the area where we hit into some issues that in the end we solved it with Istio, and we are going to go into details that what were those challenges and how we solved that with Istio. So talking about security, so what we wanted to achieve here in order to make things seamless for the users and also for those who are operating the Kafka cluster. So one thing that we wanted is that out of the box to have mTLS communication across all the services. So not just a Kafka cluster itself, but the Zookeeper cluster, which is a requirement for Kafka. Prometheus, if you are using Prometheus for monitoring Grafana, the client applications that are talking to Kafka, again to talk using mTLS to the brokers of the Kafka cluster. Now, so that was one, and even to have mTLS provided for those services that are not capable to talk using mTLS natively. As an example, up until recently, until Apache Kafka 2.5 was released, there was not possible to have secure communication, in fact, mTLS communication between Kafka and Zookeeper. So in Kafka 2.4, there was also some support for that one, but because of a bug that you were not able really to enable that. So in the end, you needed, you had to wait until Apache Kafka 2.5 and Zookeeper 3.5, as far as I remember. But the same problem existed for also client applications written in certain languages, programming languages, and not prepared to pick up configurations that enables mTLS. So we wanted a solution that provides mTLS also for those kind of services that is hard to enable mTLS or is not capable at all to do mTLS natively. The other aspect that we have in mind here is that from security standpoint, if we already are having mTLS, the certificates there should be short-lived certificates, and that should be something configurable. So it's not something like creating certificates that are valid for a year or months, but rather something that expires after 24 hours. If they have such certificates, then the question arises: how can we renew these certificates and redistribute these certificates to everywhere in such a way that we don't have to restart the impacted services, because restarting impacted services may cause service degradation or service downtime. So we wanted to do something that allows us replacing, regenerating, and renewing the certificates on the fly as frequently as we wanted, almost as frequently as we wanted. The Kafka client applications usually use a library that implements the Kafka protocol. Now, these applications can be implemented in different programming languages. Due to that, they would expect these certificates in different formats, like Java applications expect these certificates to be present in Java key stores and trust stores. Other applications expect these certificates to be in files in PEM format. So what we wanted is to have a kind of a unified way to set up these configurations, so users don't bother with and trying to understand that for every single the specifics for every single client application in order to enable mTLS. So that was another problem that we wanted to tackle with. Since we're on Kubernetes, also we thought that it would be nice just to identify our client applications by the service account they are running with. So deploying and start using, communicating in a secure way with a Kafka cluster, deploying our client application should be as simple as just deploy our Kafka client application into a namespace under a service account, and somehow magically out of the box just get mTLS and provided without any further configuration, and also to get my application identified by the service account, and then Kafka identify my workload, my client application by that service account and apply the authorization rules for that service account. And if you have also, we wanted to this to be a solution that expands across regions, across multiple Kubernetes clusters. So basically, from the user standpoint of view, deploying a Kafka client application into a Kubernetes cluster that shares that holds the Kafka cluster to be the same thing as deploying the same client application in a different Kubernetes cluster and then talk it across the cluster into the other one that hosts the Kafka cluster. So for the user, that shouldn't really matter what Kafka cluster, what Kubernetes cluster it deploys its own Kafka client application. Okay, so let's see that what are the challenges in terms of security that Kafka poses. I mean, if you wanted to implement just basically just leveraging the capabilities provided by Kafka. So as mentioned, that Kafka allows different authentication mechanisms. We decided to just go with the SSL with client certificates. In this case, the client certificate presented by the client application is expected to have in the subject field a value which is nothing else than the client's identity. So and that's going to be the principle that the ACLs within Kafka are being applied to. Now in Kafka, to set up SSL with client certificate set-based authentication mechanism, you need to provide server certificates for the brokers itself. You need to provide certificates for the workloads for the client applications. On the Kafka configuration side, these certificates, and so basically the keys and the certificates has to be stored in trust stores and key stores, which is in a JKS format, or it can be a PKS12 format. In the latest version of Kafka, there is a support for PAM format as well, but back that time it was only just JKS and PKS12. Now, how can, and these key store and trust stores have to be made available to the brokers, to the Kafka brokers, through their in a file, and those has to be referenced in their configuration file. Traditionally on Kubernetes, what you do here on Kubernetes, you can create config maps, or you can create Kubernetes secrets, store these trust stores in those secrets, mount that into the pod, and that will be available for the containers in the pod. So this is how you can pass in this configuration to the Kafka brokers. Now, one of our requirements regarding the security, as mentioned, was that we wanted to be able to work with short-lived certificates, which means that once before those expire, those has to be renewed and has to be redistributed. How would this work on a normal Kafka cluster? Basically, in this case, what we have to do is basically regenerate certificates, regenerate those key stores and trust stores, and those has to be deployed to the pods. Now, assuming that these are Kubernetes secrets mounted into the broker pods, even though we update these Kubernetes secrets with the new content of the keystone and star store, since the way how these changes are being propagated into the container, there's no guarantee that these changes will be visible right away, because the way Kubernetes implements this is that in fact, a new file will be created and a symlink is being switched from the old file to the new one. So not necessarily will be a event generated within the container that signals that there was a change to the file. This is one aspect. The other one is that Kafka itself predates Kubernetes and wasn't developed, designed in such a way that it would look for these kind of changes. So is not polling continuously these files. So this means that once we regenerated these trust stores and key stores, we are required to bounce those containers, those pods, in order to pick up the modified key store and trust store. Right? And this is something that we wanted to avoid, because once you restart your pods, you may realize that your pod is not going to be able to come up. There can be various reasons. One reason is that if there are other pods in pending state waiting for resources, so for example, if your Kubernetes cluster is overloaded, then it may happen that while your broker pod is restarting, during that time another pod is being scheduled by the scheduler, so your pod won't be able to schedule because of lack of resources. Even though if there are enough resources for each of your brokers to be restarted, and even though if you perform a rolling upgrade, so you do a rolling restart, so you restart broker by broker your pods, there might be some disruption notice at your client applications due to that that when a broker goes down, even for a short period of time, it may happen that during that short period of time there will be new partition leaders re-elected, which causes all the client applications that were connected to the broker that went down to be redirected to another broker that just took up the place of the previously restarted broker as a leader for particular topic partitions. So, in a nutshell, the traditional way how you can refresh trust stores and key stores for the Kafka configurations would require a restart of the Kafka brokers. The same kind of problem applies also for the client applications, right? Client applications, depending on what programming languages they're written with, they need, if they are running on Kubernetes, they need these kind of trust stores or key stores or PEM files to be available for them, usually via config max or secrets. The same problem applies when these has to be refreshed and because the certificate renewals and redistributed to these client applications. For each client application that have a different identity or wanting to have a different identity, you need to create separate certificates with a different value in that subject with what I just mentioned before. Now, so these are the challenges basically that may have, can cause effects that we didn't want, or at least what we wanted to avoid. And we were thinking that how can we solve all these problems easily? And you will see that Istio can solve all these problems in a very elegant way for us. And you will see that how we did that. And I think with that, I'm just handing over to my colleague Zsolt to start talking about the way we implemented and how we overcome these problems that we just mentioned about certificate renewals and having also a kind of a unified way to enable mTLS configurations across the board, or for all the services that are making up such a system.
Yeah, thanks. So basically, in a way, I will summarize what Sebastian mentioned and what was the solution for the challenges. And as you may already know, is the service mesh, and Istio is kind of a new layer in the infrastructure. And one particular issue that why we think it will help us solve these kind of problems is that it can unify this whole security layer between your applications. And so for those security challenges, it seemed like a good approach to try to combine Istio with Kafka and then provide a better solution that way. And so how this usually works is that obviously all the components that combines the Kafka cluster will have an Istio proxy in front of them, and the Istio proxy and the whole Istio obviously can provide the much needed certificates for the broker side and for the client side as well. It also can provide the renewal feature that we set as a goal to be able to quickly renew and distribute certificates for the brokers and for the client side. Now, basically, as Sebastian mentioned, it's kind of a hard way on the broker side, but I think it's much more a problem for the client side as well, because the broker side is kind of within your administrative control, more like the client side, because of the various programming languages that those client applications was built with. So how this this is why this unified layer as Istio can help with that. And it works obviously for both the client and the server side, and besides the encryption, it also provides mutual TLS. So basically, it also can help you with the authentication side as well. And so the issued certificates within Istio basically contains a SPIFFE format ID. In the format that is just visible on the slide. So basically it contains information, identity basically, about this particular workload, or more precisely about the service account in which name the workload is running in. And besides, the generic renewal functionality is also possible, to configure even in a workload basis if you want different kind of custom expiration date for sensor. And also, which is important, is that the renewal of the certificate on the client side or on the broker side doesn't really need the restart of that particular workload, and as such, there won't cause any service degradation. I just want to highlight here, and I think we can just jump onto the next slide. Is that it's just a simple architecture diagram about the main components of this of the Kafka. Basically, not every component that we are running is on that slide, but the gist is that basically all the brokers and the zookeeper that the brokers are using for storing all kinds of information are all contains an Istio proxy. And as you can see on the diagram, basically the Istio proxy is handling the TLS and mTLS side of the communication. So it's not just encrypted, but also validated or authenticated from both sides. And basically the communication between the proxy and the particular backend, so in this case the zookeeper or the broker, is still plain text. And on the broker side, it's basically really simplifies the configuration of the broker, because you don't have to deal with the things that Sebastian mentioned at the first part of the talk, but rather you have a much easier configuration as this uses plain text settings, basically.
Yeah, so basically the broker's configuration simplifies a lot, because you don't have to set up things needed for mTLS. You just configure the broker's listeners, which are the endpoints for the Kafka brokers, to be running in plain text mode, which is a very, very simple configuration.
Yes, and as it was also mentioned, it was one of our goals as well to provide, if we can, a transparent, very easy authentication, and as a result of it, authorization for the clients as well. And so now to give a bit of a detail on that is that why when the Kafka is running in a plain text mode, or let me rephrase. So when it would run, nakedly in TLS mode, then it will get a certificate, and then it would authenticate the client based on those certificates. But right now, as Istio provides basically the certificates, and it terminates the certificate on the proxy side. And as I mentioned, Kafka is running in plain text mode. Then we have a problem there to solve, is that basically provide the information that it's in the certificate and comes to the proxy and transport it to the Kafka broker side. Because that's needed for authentication, and as such is needed for the authorization as well. So basically, how this works is that the communication is flowing through the proxy. The proxy terminates the TLS connection, authenticates the other side with this mutual TLS feature, and then basically we somehow needed to extract that information and pass along to the broker, so the broker can then do the authorization based on this client authentication information. So yeah, we can go to the next topic. So how we did that to solve that issue is that we created a WASM filter precisely for doing exactly what I just said. So basically, what happens is that, as you can see on this diagram, is the client application, if it's running, within the same cluster for the sake of simplicity, it will get obviously a proxy, so it's within the mesh. It will get the client certificate, and with this, if you communicate to the broker's proxy, and the certificate it authenticates with contains the authentication information as a SPIFFE ID in that cert. And now that WASM filter that is running within Envoy, an Istio proxy, it extracts that information for the certificate and basically provides a way to pass it to the broker as client ID, basically. And then the broker can take that information and do some authorization based on that information. And obviously, there are lots of bits and pieces to do that. So we have lots of custom resources that you can use to define those in a Kubernetes cluster. But it's not, we are not going to talk about this in detail. I just want to mention it that this is basically provides a very, very easy way from and a transparent way for an application standpoint, because the client application that is on the left side of this diagram it doesn't know anything about this whole mTLS authentication and whatnot. It basically comes automatically for it. So you just deploy the application, and it's magically will be able to communicate securely to the broker. And besides that, it will be authenticated and just able to reach the resources that was authorized for it. And yeah, and also as an added benefit, or it was one of the goals as well, is that while we are actually having Istio, then we have a bunch of expertise of running Istio in a multi-cluster fashion as well, and it's really come in handy in this particular use case as well. So with this whole setup, we also have a way to basically have secure cross communication between different multiple clusters that within a single Istio mesh. Once the common trust is provided for those participant clusters, and so it's a very nice way to expand or segregate things depending on what you really want to achieve. Yeah, and so I think what we wanted to show here is that the Istio as a layer, obviously, it doesn't just provide security for us or in that particular solution. We just want to highlight this one particular area, but it also provides the observability for the communication as well, and all kinds of other things that this particular unified layer can provide. And particularly for the security, I hope that we can just at least shed some light on how easier it from this perspective is that how you can set up a Kafka cluster, how you can secure that Kafka cluster without the headaches, or basically make this whole Kafka solution in Kubernetes much easier and much more cloud native way to use. And also the Envoy that runs basically within the Istio proxy with this WASM filter as a feature and possibility. It can provide a lot of ways for everybody to expand or extend the functionality of the service mesh, even in a way that we did, or for the observability, or really in a bunch of ways.